In this video, we're going to begin to talk about some circuitry issues that I need you to be aware of for when we start to talk about robots and embedded systems. So let's take a look at some of the circuitry things we need to be concerned with. The first thing is a term that is very often confused, and I'm just not going to go into it more than to give you the basic concept, because as you play with some of these systems, it'll start to make more sense to you. And I may come back and do a whole video on just this, but for now I just want to introduce the concept so that it can kind of sink in, if you will. And you'll see why that's kind of a dad joke at the beginning of this, because we're talking about sourcing and syncing. Okay, if we have a system where we have a circuit, where we have some sort of a differential or a battery, and by the way, you'll hear the thunder because I'm doing this lecture in a lightning storm. So we have plenty of electricity running around the atmosphere tonight. But you've got a source going through a bulb and a switch to the ground, okay? When the switch is open, this thing is constantly attached to the source, okay? So it's constantly attached to the source. So when we close the switch, the connection to ground will sync this to be a closed system so that it then works, okay? So this is called a sync circuit, counterintuitively, because it's constantly attached to the source. So the syncing is what makes the circuit complete to allow the electrons to flow. Okay, so that is a sync circuit. Now to flip this, all we have to do is put the switch on the other side of the light bulb. So in this situation, if the switch is open, we're constantly connected to ground. So this thing is constantly grounded, all right? When we close this switch, we are sourcing it by giving the source power to the bulb to then go to ground, okay? So that is known as a source circuit, okay? So if it's constantly attached to the power, we're going to sync it to get it to turn on. And if it's constantly attached to the ground, we're going to source it to get it to go to ground. Okay? That's all I want you to worry about for syncing and sourcing for right now. Okay, the next thing we need to be very familiar with, and I know that you've probably used these terms, but you may not be completely clear about what they are. We're talking about an analog circuit or an analog signal and a digital circuit. Okay? And I want to visually show you what moves along those circuits, okay? So we'll start with analog, and it's basically sine waves where the amplitude changes, okay? And this is my voice right now, is an analog sound. You're hearing it through your speakers, okay? We'll talk about what happens to it between me and you, okay? But it is an analog signal, okay? So as I raise my volume and voice, and if you've ever played with any kind of an amp, really anything analog, record players are analog, okay? The needle vibrates, you get the sine wave, okay? That goes to, if you're on a pure analog turntable through an amplifier out to speakers, this analog signal just gets transmitted through all those devices as an analog signal, okay? And I'm going to tell you something that I think is kind of funny at the end of this video, but an analog signal to analog speakers, you're going to get all of the sound, okay? It's going to be what you hear is the sound, okay? Digital is a signal that is basically a square wave pattern that represents bits of information. So it's either a 1 or a 0, okay? There's 1, there's 0. Now, when we deal with the amplitudes and the power, 0, the circuit would be off. We couldn't tell what was going on. So it's typically a high signal and a low signal, and that could vary based on the equipment or what the design is, or what you're doing. But basically, it's a square signal that is giving us bits of information, okay? So that's important to keep that difference. Analog is all of the sound wave, and this is an interpretation of the sound wave, okay? All right, so let's talk about some of the differences. In an analog circuit, like we said, it's continuous wave, they're sine waves, and they are recorded as they are. Okay? Now, sound waves can deteriorate. Okay? If I were to put a piece of foam between myself and that microphone, it would be muffled. The sound, you'd only possibly even hear just the sound that was bouncing around to get to the microphone. Okay? So it can deteriorate, and it's sensitive to other noises. Okay? For example, while I'm talking, you may be hearing the rain or the thunder that's occurring, and that's actually noise, where my voice is the signal, and the signal to noise ratio can vary based on how much interference or other noises there are. Okay? And it's not really flexible in its implementation. You either hear it or you don't. Okay? Digital, oh, and here's some examples. Human voice, analog speakers, record player. I already said that. All right. So a digital circuit. This is a discrete time square wave. All right. And it's ones and zeros. All right. Different amplitudes. And it can be noise immune. Remember, I said a digital signal to your television through HDMI actually has a system. It's not really encrypting, but it's a digital packeting system where the TV knows it got the full signal from what sent it. Okay? And Dolby, by the way, does the same thing with the audio track. All right. So it can be noise immune. Doesn't have to be, but it can be. And it can be without deterioration, like I just explained. Okay? And it's flexible in how you interpret it because you're getting ones and zeros. You're getting binary information, so that can be processed. Okay? All right. Some examples of that: CDs, DVDs, computers, digital players, this thing that plays my music, okay? My phone, all of these are digital signals and good examples of those waves. Okay? Now, we also use signaling for logic gates in the transistors of a chip. Okay? And we will send signals to actuators and things on a robot and stepper motors and signals that need to be read. But another use is on NAND gates, NOR gates, AND gates, OR gates that make up the circuits that build us binary half adders and adders that allow computers to make calculations using binary. Okay? And what happens is if a particular gate doesn't have power to it, there's no input to a particular gate, the voltage across that gate can drift high or low. So depending on what type of gate it is, we use what's called pull up and pull down resistors. It's just a resistor placed in the circuit in a position that allows it to do one of two things. In the case of a pull up resistor, it ensures a known state for the signal. So that keeps the logic gate high. So if you think pull up, it's high. It's going to keep that gate high, basically like at a 1, okay, if the switch is open. Now, if the switch is closed, it's going to do whatever the switch needs to do based on the signal it's getting. But if the switch is open, it's going to keep that gate high. All right? Conversely, a pull down, well, let's talk about that. We use those for logic gates, wired OR functions, so it's combination logic. Okay? Now let's talk about a pull down. Again, it's ensuring a state if there's no input to the gate at a particular point, and it's going to keep it low to ground when there's no input. Okay? And that is used in CMOS logic gates, and inputs are voltage controlled. Okay? So it has to do with the voltage, and so in a CMOS logic gate, it needs to be to ground when there's no input on that gate. Okay? So pull up and pull down, just make sure that the gates work properly so that if there's no input to the gate at a certain point, it's either going to be high or low based on what the needs of that gate is, to make sure that we have a usable state on that gate, because the voltages can drift up or down if there's no input there. Okay? And they tend to drift in the wrong direction. So we have pull up resistors to keep it high, and pull down resistors to keep it low whenever we need it. Okay, and again, that's all I need you to know for those. All right, now, Again, they make sure that the input to the gates are correctly biased. That means high or low. Okay, and they're not floating all over the place when there's no input condition. So there you have it. Okay, now I want to talk about converters, because as I'm talking to you, my voice is being converted analog to digital. Okay, so let's talk about these. I have an analog wave, the words that I'm spewing, okay? And it's going to go through this analog to digital converter. The kind of the slang for it is it's an ADC, okay? And it's going to convert my voice to ones and zeros, which are being recorded. Now, where does this happen? The microphone brings this in, and then there's a chip that does the conversion to turn it into a digital signal, and then it's stored on the memory chip as part of the file format of the MP3 or whatever this thing's recording. Okay? So, it's typically a metal oxide semiconductor integrated circuit. Okay, so it's a chip on a circuit board that's made of metal. It's a metal oxide semiconductor, and it's a chip. And what it does is, if you've ever had calculus, it samples this wave. And the more it can sample, the higher frequency you can sample, the more accurate this is going to be. Okay? So if you have less sampling, you have a rougher sound. All right? Now let's talk about going the other way, what you're hearing. Because it's going to go through, I'm going to store it, edit it, put it up on YouTube. YouTube's going to send the file down to your computer. You're going to hit play. And through your earbuds, your speakers, your television, however you're hearing my voice, okay, and seeing me, okay, those are going to be analog signals that have been converted to digital. Because even the video of me moving right now, like, hi, okay, that's being converted to digital bit patterns from the camera sensor, which is also being digitized, okay? So we're going to start with the square wave, and it's going to try to put it back through a digital to analog converter. So it's going to recreate as best it can, okay, and it's got limitations on frequency and things as well. And it is also a metal oxide semiconductor integrated circuit, and it's going to convert it back to that signal so that the speakers, whether it's in your earbuds, in the back of your television, your sound bar, whatever it is, those speakers can recreate the analog sound so you can hear it. I've had students ask me, is our brain an analog to digital converter? And the answer is really no. Okay, I'm not a neurologist. I don't play one on TV, but we have electrical signals, but just having electrical signals in our brain doesn't mean we think digitally, okay? We've got analog brains, okay? When you say something, if I hear it correctly, I hear it analog, okay? My eardrums are moving to transmit the analog signal electrically. Record players connected to analog speakers, it's still electric transmission of the waves, okay? It's not converted to ones and zeros, all right? So that's a digital to analog converter. Now let's look at some of the differences between them, okay? They both convert signals. They both are rated on resolution, okay, which is kind of their max sampling frequency. How many times they read that analog wave to go back and forth. And most are implemented as ICs like we talked about. And they're on MOS chips. And they're both implemented with both analog and digital circuits. Now why do I say that? Because one's not analog and one's not digital. You need both on both, because I'm going on this one from analog to digital, and I'm going on this one from digital to analog. So I need both on both, okay? That's important. And by the way, this camera that I'm talking to has both in it, okay? Because it can play back for me, and I can hear myself if I hit play on the camera. So it can go in one direction, and it can go back in the other. That's how convenient, small, and easy these things are, okay? Now, microphones and digital cameras are the best examples, especially on an assessment, for you to pull out for what's an analog to digital converter, right? The video or the camera image of a digital camera and microphones, all right? And the other way around is your CD players, your sound cards, your digital music players, but you're not wrong if you say a digital camera, as long as it can play it back, which they all can. Okay? Now, one of the things I want to talk about that's kind of funny to me is I go into these stores and I see these record players, okay? As my daughter once called them, my big CDs when she was 7, okay? Because my vinyl, all right, you can play it, but it's got digital speakers. Well, the purpose of having vinyl, if you're old school and vinyl is making a comeback, all right, is because all of the sound is present on those sine waves. When you convert to digital, we still have not invented high def audio. There's still limitations on the ADCs and the DCAs, or the digital to analog, okay? The DACs, because we can't store enough of the wave to get it all. So that's why purists and audiophiles, if you will sit there and play vinyl on analog speakers because it's better sound. It's all of the sound. When you convert to digital, it doesn't sound as good, okay? Scientifically, it doesn't sound as good because you're not getting all of the information, okay? We don't yet have the system. We're getting closer every day, but we don't have it yet because it would be a very, 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 very big file, okay? So you're kind of teasing yourself if you're listening to a record on digital speakers. You're not getting the effect. So you want to make sure if you're going to get a record player, all right, and you're going to hook it to speakers, make sure that it's analog all the way around, okay? Get yourself a set of analog speakers. You may even need an analog amp to analog speakers so you can drive the speakers. But you want to be pure analog end to end, or you're not getting the benefit of the vinyl, okay? And you would be surprised. Well, you might not be surprised. I am always surprised at how many people do not understand that, okay? So now you're a little smarter when you go into the record store, okay? And there's some big dude in the back going, oh, this is pure sound, right? You can have a conversation with him because now you know. He's not wrong. Digital sound is less. Now, it's really, really good, but it's not the same as the analog sound, okay? Now, in the next video, we're going to talk about sensors, which gets us even closer to playing with some of these toys. So this should be a lot of fun, and I'll see you on the other side.